Hi, I'm Nico Nierenberg, CEO of Persyst. In this video, I will be doing a short demonstration of Persyst 14, the latest version of our software. This demonstration will be done using a standalone version of Persyst, although frequently you will be using Persyst in an integrated fashion with the EEG manufacturer's software. This is the new standalone database window, which stays available after opening an EEG file, allowing you to easily manage multiple patient records. If you use Persyst with the EEG manufacturer's software, you can open EEG files using their database in the usual manner. But one advantage of the Persyst database is that it is able to read almost any EEG format and organize them all combined in one database. We see the list of patients here. I'm going to open a 24-hour epilepsy record. The view you are looking at now is called a trends view. On the trends view, time is on the x-axis, just like an EEG page. But unlike a typical EEG view, we are looking at 2 hours of the record. The amount of time that is represented can be adjusted, and I'll be doing that later to focus in on some specific features of this record. What you are looking at vertically are sets of different trends that indicate different things about the EEG, and I will walk through what some of those are. You can customize different combinations of trends into what we call panels. Depending on the type of patient, there might be different combinations of trends that you are interested in. I'm going to use what we call the Versus Baseline Comprehensive Plus panel. It shows a wide range of trend types and features. Starting at the top of the page, we have artifact intensity, showing how much artifact and what type of artifact is present in the EEG at this point in time. Darker colors represent the presence of more artifact. If we look at the y-axis, we can see that the top line represents the amount of EEG. Second blue line shows the amount of vertical eye movement. And the third shows the amount of lateral eye movement. So very quickly we get some useful information, which is that this patient is awake. The next part of the panel is seizure detections and seizure probability. They are blank on this page as there were no seizures during this time period. As we go through the file, we'll encounter some seizure events later. I'll mention now that the new seizure detector in Persyst 14 performs better than the older Persyst 13 seizure detector by an order of magnitude. In a recent publication, the Persyst 14 seizure detector was shown to perform within the same range as human expert readers. You can find this publication on our website. The next trend is spike detections. Persyst 14 spike detection still has the same high level of sensitivity with low false positives that you could expect in Persyst 13. Since Persyst 13 was released, there have been 2 publications showing that the Persyst spike detector also performs within the same range as human experts. We'll get to some more interesting aspects of spike detection later, but one important feature for both the spike and seizure detectors is that you aren't going to get hundreds of false positives, making it more time-consuming than it's worth to review the events. The next line has to do with spike rates, and I'll get to that in more depth in some other records. The next trend is the rhythmicity spectrogram, which is unique to Persyst. The trend is divided into left and right hemispheres. We look at the right on the y-axis, and there's a scale going from 1 Hz to 25 Hz. It is calculating the amount of rhythmic activity by frequency from low to high. The rhythmicity spectrogram is particularly effective for locating many types of seizures. There isn't much happening during this 2-hour period, although you can see a clear posterior dominant rhythm during much of it. The next trend is the FFT, sometimes called a CSA. The FFT calculates the EEG power overall at different frequencies. Again, it is divided into the left and right hemispheres. And the y-axis represents frequency from low to high. The color scale reflects the amount of power at each frequency. Next is the asymmetry spectrogram. This trend is measuring the power difference between homologous electrodes across the left and right hemispheres at different frequencies, which can be used to assess how symmetrical the EEG is across hemispheres. And again, the y-axis goes from low to high frequency. The colors in the asymmetry spectrogram are like the American political system, where blue is left and red is right. Darker colors indicate greater asymmetry. There isn't anything notable on this page. The EEG is roughly symmetric here. The next is the amplitude integrated EEG display. Again, where the left hemisphere is represented by blue and the right by red. Because the left and right are currently overlapping, it results in a purple color. Next is the suppression ratio. This patient's EEG is not suppressed, so the ratio will hover around 0. Underneath this is the heart rate trend, which is new to Persyst 14 and utilizes the EKG signals obtained as part of the EEG recording. With the continuous heart rate trend displayed synchronized with the rest of the trends, you can see changes related to seizures and other EEG features. Finally, at the bottom, we find the versus baseline trend, an important new addition to Persyst 14, which allows the user to compare data with baseline data from the same patient. This is useful for detecting and monitoring progressive changes that may not be immediately apparent in the raw EEG signal. The color and saturation represent how much statistical change, expressed in z-scores, has occurred in the EEG at that point in time versus the selected baseline. The two-ended color scale is increasingly pink for positive z-scores, a statistical increase in power compared to baseline, and increasingly green for negative z-scores, a statistical decrease in power compared to baseline. And white indicates no change compared to baseline. The current setting is for a range from -6 to +6 z-scores. The baseline is either automatically generated or can be user-defined. It is indicated by the bar at the bottom of the trends page. So that is one set of trends for Persyst 14. The user has the ability to customize their own trend panels to meet their clinical needs. What I'm going to do now is move forward through the file using this button on the bottom right. I'll be moving forward 2 hours at a time. And that shows how quickly I can review this kind of record. So I've just moved forward 2 hours and still nothing is happening. The patient is still awake, as you can see at the top of the screen. I move forward 2 hours again and things start to happen. If we look at the top of the screen, at the artifact intensity, we see that the artifact starts to drop off. And this patient is getting drowsy and falling asleep. And then we start to get some spikes. The spike intensity increases. So you're seeing spikes, maximal on the left, indicated by the blue color, at increasing rates, and then the patient has a seizure. The patient wakes up briefly and then falls back to sleep. And the spikes continue, as we can see, looking at the rest of the page. If we look at the other trends, we can see related things happening. I'm going to change the time scale on the trends view to 1 hour so we can see that a little bit more clearly. Again, this is the same pattern, just zoomed in a little bit. Looking at the rhythmicity spectrogram, you can see the rhythmic activity moving from higher frequency to lower frequency. And it is predominantly on the left. The pattern of seizure evolution will often look the same for seizures within the same patient, a kind of signature. Of course, you won't agree with all the events the seizure detector marks, and similarly, it may not mark everything you consider to be a seizure. But when you're looking at the EEG, you might notice this kind of pattern on the trends at the same time. That means you can look through the trends after that to quickly find similar patterns. The FFT shows the same pattern moving from high to low frequencies. And similarly, the asymmetry spectrogram shows that the seizure is predominantly on the left. Immediately after the seizure, we see that the left has increased in slow activity relative to the right, while the faster activity on the left has been suppressed. The AEG shows this seizure as well, with the blue line above the red line indicating a higher amplitude on the left than the right as a result of the left-sided seizure. The heart rate trend shows a short decrease at seizure onset, followed by a rapid increase, slowly returning to baseline after the seizure. In the versus baseline trend, we see an increase in activity across both hemispheres, with a greater increase on the left. Immediately after the seizure, there is an increase in delta activity, which then returns to baseline. So now I'm going to move to the EEG at the same point in time. I'm going to do that by setting the cursor at the onset of the seizure, and I'm going to switch over to the EEG view. This puts us at the beginning of the seizure. Seizure onset is somewhere in this area. You can see how the trends align with the seizure activity in the EEG. As often happens, the EMG artifact obscures a significant portion of the EEG. What I can do with one click of a button is turn on artifact reduction. It removes the EMG artifact, and we are showing it in the background in a light gray color. I can see right through the EMG, and this is not done using a high frequency filter, and the signal is not being distorted. One way to see that is if you look at this channel. You'll see that there's not a lot of EMG in that particular channel. And if I turn on the artifact reduction and turn it off again, the signal is not being altered. This is all done by something called blind source separation, where the signal is broken into its constituent portions. We use an algorithm to determine which portion is EMG and remove that portion and put the rest of the signals back together. The result is a nice, clear picture of what is happening. Artifact reduction also detects and removes a lot of lateral and vertical eye movement. This is a very powerful feature, and it works across a wide range of EEG and is useful even when you are just reviewing EEG separately from the trends. Of course, we also use the artifact reduction feature in the trends. When we were looking at these trends, the artifact reduction was turned on. This means that the trends are computed using mostly cerebral activity and not eye movements, EMG, and electrode artifacts. Those are all removed prior to the trends being computed. This makes it much easier to interpret quantitative EEG. If I turn the artifact reduction off, this is what the picture would look like. Everything would be a lot less clear. These large artifacts at the beginning of the page are, as we have seen, actually not a seizure. It's just electrode artifact. This is the clear picture you get only from Persyst. No other quantitative EEG detection and trending software has artifact reduction. Another feature of Persyst 14 is spike review. In spike review, we load all the spike detections from the record, in this case 24 hours, and summarize them by where they are considered to be maximal. We present them so you can see a summary as well as the individual detections. This can provide a very quick review mechanism for the spikes that were detected. In this case, we see that there are 1,099 of them, the vast majority considered maximal at T3. And you can see the averages of the spike detections. In Persyst 14, we also have a new way to mark spikes manually. Any spikes you mark manually also appear here in the spike review summary in their own groups. I can turn the voltage map on, and I can look at individual detections by clicking on a group title. If I want to see those detections in the record itself, I just click on them, and the EEG moves to that part of the record. This is a very quick way to review the large number of spike detections that you can get in a long record, and you can save a lot of time. Another feature of the spike detection functionality in Persyst 14 is the ability to do automated spike counting. To show you this, we're going to take a look at a status epilepticus in sleep case. These frequently require hand marking to determine the spike rates. This record has been marked by Persyst 14, and as you can see, the spikes are very consistently marked. The Persyst Spike Index tool is for spike counting. We have marked a section of the record as slow wave sleep, and we have determined that our epochs are 10 seconds and the threshold will be 7 spikes during an epoch. So then all we have to do is click calculate. And Persyst immediately calculates the number of epochs that exceed that 7 spikes during that slow wave sleep period. And that's 94% of the epochs. There were 2,000 spikes during that period of time, a little over 1 spike per second. This can obviously be used not just in this kind of case, but in any case where hand counting of spikes is interesting. It can save a lot of time and increase consistency from the fact that you don't have variation from one human reader to another on different days. The spike counting from Persyst 14 will be consistent across those days. Another interesting feature of spike detection in Persyst 14 is the way it can work on ICU cases. So here we have a lateralized periodic discharge case. And as you can see, Persyst is consistently marking discharges. Looking at the bottom, you can see that it is also accurately determining that these are predominantly on the left side. And so these are lateralized periodic discharges as marked by Persyst. To support the long-term evaluation of that, we can use spike trends. As we saw briefly in the epilepsy record, this includes a color code of which side the spikes are maximal. The blue continuous line indicates continuing lateralized periodic discharges on the left side. This gives you a good indication that this is continuing without having to look at every page of EEG. Here is another record. This is a generalized periodic discharge record. Generalized discharges are marked in green. And red would be on the right, and occasionally the software is determining that they are on the right, but these are pretty much generalized discharges. And if I go to some part of the record like here, you can see them continuing with Persyst consistently marking the periodic discharges so that they can be tallied up for the trends. Again, a very nice strategic overview of what is happening in this case without having to look at every page. You can see that the generalized periodic discharges are continuing. Finally, while we discussed the versus baseline briefly in the seizure example earlier, This trend can be particularly important for ICU cases. Here is a file recorded in the neuro ICU of an older patient who was under observation after experiencing a large right middle cerebral artery ischemic stroke, and so was being monitored due to a risk of increased intracranial pressure and seizures. Knowing the patient has a right-sided stroke, it makes sense that the overall power of the EEG is asymmetric, as indicated by the dark blue color on the asymmetry spectrogram. You can also see this in the FFT and AEEG trends. There is a cyclical oscillating pattern of brain function that is easily seen in the AEG trend and interestingly echoed in the heart rate trend. As I move forward in time, the versus background trend shows a further decrease in amplitude in both hemispheres in the higher frequencies. I'll place my cursor here before the change. And then switch to the split screen view so we can see both the trends and the EEG. Here is the EEG before the change in amplitude. And if I click here in the area where we see the decrease, here's what the EEG looks like after the change. Between the two time points, it is clear there's a substantial decrease in the fast components on the left in the upper beta, alpha, and theta range. The right, which started out quite low to begin with, decreased even further in those same ranges within this period of time. So what is going on here? Due to the stroke, the patient was obtunded, and so any clinical changes that corresponded to the changes in the EEG may have been difficult to detect at bedside. Despite the fact that we can clearly see the extent and significance of the change in the versus baseline trend around 1305, it wasn't until roughly 1400, 55 minutes later, that the clinical team suspected that the patient was possibly becoming less responsive and that it might be due to increased intracranial pressure. As a result, they gave a test dose of mannitol around 1425. To relieve the intracranial pressure. After they gave the mannitol, it was 15 minutes later, around 1440, they felt the patient had somewhat improved clinically, i.e. the patient had regained the previous level of responsiveness. But the versus baseline changes show that the EEG improved immediately after the dose of mannitol. The fact that the patient's EEG returns to their initial post-stroke baseline immediately after receiving the dose of mannitol supports the hypothesis that the patient's worsening clinical state was indeed related to increasing intracranial pressure. Indeed, the heart rate oscillating in step with the oscillations in brain function could also be related to the patient's increasing intracranial pressure. In retrospect, we see how the new versus baseline trend can support reliable recognition of important changes in the EEG. They may happen slowly over time and otherwise more difficult to recognize, and therefore how this important new versus baseline trend could allow for clinical decision-making sooner in some ICU cases. This has been a quick summary of Persyst 14. There are many more features and many things that can be customized to present different EEG features the way that you would like. We'd be happy to go through that with you, and we will be doing other videos going through other specific features in depth in the future. Thank you very much.